So far, we've only been looking at compounds with one chiral carbon, so let's see what happens when we start having multiple chiral carbons. Let's take a look at this structure first. You can tell that we have two chiral centers that I'm noting here with the stars, and we're going to look at each of them individually to determine the R and S configuration. It's obvious to tell that if we are looking at this chiral center here, that bromine takes top priority and hydrogen takes bottom priority. And then if we go out here, we have a carbon in this direction with only hydrogens on it. And in this direction, we have a carbon with a bromine on it. So this is automatically going to be group 2, and this is going to be group 3. And so that chiral center is going to get the R configuration. You can do the same type of analysis with the chiral center here, and you will see that once again you get the R configuration about that carbon. So let's draw the enantiomer of the compound. Its non-superimposable mirror image. And let's do the designations. Again, we have 1, 2, 3, and 4. And so this is going this way. This is an S configuration. 1, 2, 3, and 4. Again, going this way. So we have an S configuration. So we would say that this is the RR enantiomer on the left, and this is the SS enantiomer on the right. And just like we would expect, because they're enantiomers, they should be exactly opposite in configuration. And when there are multiple stereocenters, the enantiomers have to be opposite at every single chiral carbon. Let's take a look at this one. Notice that the configuration is the same on the carbon on the left, so it should be R, just like it was R over here. However, if you take a look at what's going on the carbon on the right, they're exactly opposite. And so since this one was an R, we can assume that this one is an S. So when you have a situation like this, where they are opposite in configuration at one chiral center, and they're the same in configuration at another chiral center, these are not enantiomers, but they are what we call diastereomers of one another. So if it's not an enantiomer, but it's a stereoisomer, then it has to be a diastereomer. Let's look back at that RS configuration and draw its enantiomer. And so you can see if I draw its mirror image, I'm going to come up with the SR configuration at those carbons there. But you see that if we take each one of those enantiomers with the SR or RS configurations and we rotate them around, so here we've rotated this bond to this orientation, and here we've rotated this bond to this orientation, and what we actually have is the same structure twice. Compounds like this that have more than one chiral center but end up having an overall plane of symmetry are what we call meso compounds, and they have no enantiomer. The enantiomer is actually redundant. If you were to draw it, you get the same structure again. So go back to our definition of a molecule or a carbon that has a plane of symmetry. We say that it's achiral. And so this is an example of, even though there are multiple chiral carbons, the overall molecule is not chiral. And this is just one more look at the meso compound with its quote-unquote enantiomer, which is really just the same structure again. So meso compounds have no enantiomer. They are achiral. Here's another example of a meso compound. We can identify two chiral carbons, one in the R configuration and one in the S. But since there's a plane of symmetry overall, this is an achiral molecule. Notice that meso compounds, when you're comparing with two carbons, for example, those two carbons must have the same 4 groups around them, but they have exactly opposite configurations. And so if you look at the set of enantiomers that you would get from the meso compound, they're actually redundant, and so this is achiral. So let's take a look at this again, the RS mesoisomer. And now let's flip one chiral center. We'll invert it, and we will make it R, and we'll leave the other one alone, and it's still R. And the relationship between these two, because they're not opposite at every stereocenter, is that they are diastereomers. On the other hand, if we draw the mirror image of this RR isomer, we now have the SS isomer, and these two are enantiomers. So there's a formula that you can use for calculating the possible maximum number of stereoisomers that a given structure can have. And so for every n number of chiral centers, you can have 2 to the n possible stereoisomers maximum. So for example, here we have 3 stereocenters, and so we have up to 8 possible stereoisomers. And so the isomer that was on the previous slide is what we would call the RRR stereoisomer, because all 3 of the chiral centers are in the R configuration. I do want to make a note here that there is a shortcut that you can use. You have to be careful with this, but when group 4 is facing towards you, whatever answer you come up with is going to be opposite. So in this particular case, hydrogen group 4 is coming toward me, and I'm getting a counterclockwise rotation, which would indicate S, but since group 4 is coming out, this is actually an R configuration. Be careful with this, because it does not work if group 4 is in the plane of the paper or the screen or whatever you're looking at. It only works if group 4 is coming towards you, but you can use that as a shortcut. So if I asked you to draw the enantiomer of this RRR isomer, you would simply need to draw the compound that would be opposite at every chiral center. And so if you drew all of the chiral centers inside out, so to speak, and made everything that was coming forward go back and everything that was going back come forward, you would end up with the SSS compound, which is of course the enantiomer of the RRR compound. If I asked you to draw the SRR diastereomer of this compound, you would only need to invert the first stereocenter to go from an R to an S configuration. And so you can see here I kept these two the same and then just inverted this first one to come up with the opposite configuration. If we were to list out all of the possible stereoisomers of this compound, the combinations we would come up with would be the RRR-SSS, as we saw. These are, of course, enantiomers. The RSS-SRR, these are enantiomers. The RSR-SRS, which is, of course, a set of enantiomers. And then RRS-SSR, which are enantiomers. Each pair is an enantiomer, but if I were to describe the relationship between any of these pairs to another pair, so for example these two, these are diastereomers. So when they're not opposite at every center, then it's a diastereomer. So let's now take a look at that cyclic compound that we saw in the last video. And on these chair structures, you might find it useful to draw in the hydrogens on the chiral carbons before beginning to assign them. You also might find it useful just to kind of pull out the carbon that you're interested in away from the ring and draw it separately. And so what I have here is, of course, the chlorine that was here, the hydrogen, and then I have the C with an OH on it that corresponds to this one. And I have a CH2 group over here that corresponds to this CH2 group. And you might find it a little more simple, a little less daunting of a task if you break it down and just look at that one carbon. And then you can just prioritize those groups as necessary. And so you can see we come up with a 1, 2, 3, 4 prioritization. You can simplify that even further by just getting rid of the groups and keeping the numbers as we discussed before. You can do the same thing with the second chiral center and draw it out like this. And then number them accordingly, 1, 2, 3, 4. And finally, again, simplify the structure just to make it a little easier, a little cleaner to look at. And hopefully you would be able to come up with these two configurations about the chiral centers. If you need to go back through those last few slides slowly and pause and maybe use a model kit, you may find that a useful exercise to practice with chair conformations.